So this is the class on computer systems analysis. Very first class, and we will be spending time on telling you about what we are going to do in the rest of the year, rest of the semester. So 5 parts of this first lecture. What is this course about? What are we going to cover? On what time frame? And a project. Some of you have taken my previous graduate courses. Exactly same format. We have a project and grading. So the goals of this course, basically I have designed it to be the most comprehensive course I can think about performance analysis. I started out as a performance analyst myself at Digital Equipment Corporation long time ago. And one thing I found that the things that we used at the company were not taught at the school. And the things that were taught at the school were not really used at the company. So there was a big mismatch. So I sat down and wrote a whole book on what is important. The book is called The Art of Computer Systems Performance Analysis, and that is the textbook for this course. And the book is actually won the Best Computer Systems Award from someplace. I think Computer Press Association. So it has been a very famous classic book, and it is 20, I don't know how many years, 1991, 21 years old, but it still sells very well. Anyway, so the reason I said all this is because I want to make sure that you understand that this course is different in that we try to concentrate on what is important out in the real world. And throughout this course, you will hear those kinds of things as to how to really do the things for the real world and not just for writing a paper. So this includes 3 parts or 4 or 5 parts actually. It turns out that most of the courses that are taught on performance analysis, they either just talk about queuing theory and be done with it. Queuing theory is the only analysis method that they know. Or they will just talk about simulation. And if they are very hands-on people, then they will talk about measurement. But there are very few courses. I haven't seen any courses on measurement. And the word experimental design, nobody in the performance analysis community had heard about until we brought it out. And so this course actually covers all those 5 parts: measurement, statistical modeling, experimental design, simulation, and queuing theory. Now that is a lot. That's a lot, and we will have to do that with joint effort. And you will have to do some reading, and it's a very easy to read book. If you have gotten the book, you can read it, and you will see that. And then some here. How to avoid common mistakes in performance analysis. So there are some things that I noticed during my career as a performance analyst in the industry, and I want to make sure that we avoid them, and we will talk about that. That is the next lecture actually, right after this. And since this is a graduate course, it's advanced topics. There's a lot of independent reading and writing, and in particular there is a survey paper you have to write in addition to the exam. So the project or the survey paper will talk about that. That really teaches you how to know about the latest things which are not in the books. Because most of the things today are not in the books. Believe it or not, by the time you write the books, they are 3 years old, and by the time the things are already used, out of date. So now more than ever, it is important that we be able to research things online and learn fast. All right, the internet has made several things easy, and one of them made it easy is writing papers. But reading is not very easy. Reading is still you have to do manually, and writing and publishing is very easy. So we got to read. Book we already talked about. Objectives. So what will you learn? You will learn how to specify performance requirements. And that is the first thing. If you are designing a product, or if you are, in the research world probably you don't start there, but in the real world, first thing you have to do is set up the requirement that this computer I am designing, or this database system I am designing, or this whatever I am implementing will be twice as fast as this competition. Right? And so how do you specify the requirements? Then you will have to sit down and write down what my alternatives are and then compare those. And so we'll teach you how to compare 2 or more systems. And when you have a system, there are parameters, there are things that you can change, so how to tune them. And find the performance bottleneck. And that is one of the key things I will teach, or I want to emphasize throughout this course, is that the bottleneck is the key. If you want to improve the performance of anything, first thing you need to find out what is the bottleneck and work on the bottleneck. Because if you make the bottleneck twice as fast, trust me, your performance will go twice as fast. That's it, period. No more mathematics required. If you work on anything else, you can make it 100 times faster, but the performance will not go by 1%, may not go by 1%. Because the bottleneck is still the bottleneck. All right? So the first thing is the bottleneck. Characterizing the load on the system. So first thing is, what is the real workload to use? And so if you are going to use any simulations, if you are going to do any analysis, if you are going to do any measurement, you need the right workload, because otherwise it is garbage in and what? Garbage out. So if your input is just out of the air, you could as well take the output out of the air. Right? So it's important that we take the right workload. Determining the number and sizes of components in capacity planning. So in some places, if you are particularly in an organization where you have to purchase things, you have to worry about how fast things to purchase. Obviously, money is in short supply, regardless of where you are, whether you work for a bank or International Monetary Fund. You need to worry about getting the right sized computers, a right sized equipment, because you cannot just say, well, get this fastest thing. I mean, everybody cannot afford Ferrari. They have to find the right car that can work for their budget. Right? Predicting the performance at future loads, and then forecasting. So all of these things will be covered. Now, before I go more into detail, there are 3 terms that I will be using very often, and you have to understand those, so I'm going to explain those. First is system. Now, when I say a system, it could be any little thing or it could be any big thing. It could be any collection of hardware, software, firmware, anything. So for example, if you are just writing a search algorithm, that's your system. If you are designing a database system, that's your system. If you are writing a software for some sensor network, that's your system. So the system is something that you are studying. All right? So don't think about the system as being bigger than something. Obviously, there are things outside your system, and they affect the performance, and you have to worry about them. But things that are in your control, that is the one. Metrics. We'll use the word metric. Metric is how you compare, how do you measure the performance? How do you characterize the performance? So for example, for a computer, you might want to say, well, I want to see how fast some particular program runs. That will be your metric, that it runs in 2 seconds. Another computer runs in 3 seconds. Or how fast the response comes back for the user, or how many transactions can it do, 200 transactions a second, or how many searches can it do. So depending upon the system, you have to select the right metric. Workloads. Again, we talked about the workload. Workload is the input that basically goes into the system so that you can put it to the right load. So the request made by the users of the system. So we'll use the word system, metrics, and workloads. Now, this will become even more clearer as we go to each chapter. There is a whole chapter on metric, there is a whole chapter on workload, and there is actually a part of a chapter defining the system. All right, so there are 6 parts of this course. Part 1 is just the overview that we will do mostly today. Second part is measurement techniques and tools. So that is how you measure the performance. Third part is probability theory and statistics. So there we talk about lots of random numbers. Fourth part is experimental design and analysis, and actually there is a slide on each of these in the next few slides, so I'm not going to go through that. I will go through them as we come. Experimental design and analysis. Fifth is simulation, and sixth is queuing theory. So performance evaluation, we talk about actually the whole introduction that we are doing right now. Then we talk about common mistakes and how to avoid them. So I made a list of over 50 mistakes that I have noticed people made, and I wrote them down, and we can probably add to the list. But basically we'll talk about those, and then selection of techniques and metrics. So the first thing we'll talk about is what technique out of all these 4 or 5 techniques we're talking about. Should we use statistical modeling, should we use measurement, should we use simulation or queuing theory? Those are actually 3 alternatives: queuing theory, simulation. Actually, queuing theory and statistical modeling probably go together. So we generally call modeling. So modeling, simulation, and measurement. 3 techniques. And metrics. What performance criteria we will use. So here's the first example. What performance metrics should you use to compare the performance of the following systems? 2 disk drives, 2 transaction processing systems, and 2 packet transmission algorithms. So all of you know about the disk drives. Let's just ask you, and you tell me, if you were to compare 2 disk drives, you're just in the market to buy a disk drive, how will you choose one? Given that the rest of the other things are similar, like in this, the common, if you are looking for a 500 gigabyte, you're looking at 2 500 gigabyte drives, right? So how will you select? Read and write speed. So that's your metric, is how many megabits per second, how many bytes per second, and read and write speed. Good one, yeah.
The energy requirements.
And he is worried about the green, so he will say how many watts per minute or hour, how many watts does it use, basically, not per. All right, what about how often does it break? Don't you go and read the reviews on Amazon before you buy it? Because that is not in the seller's specifications. It doesn't say that it breaks every 3 months, right? How do you find that out? By going and seeing how many people have given 1 star, what percentage of people have given 1 star, because those are people who just found it really not working, right? So reliability. So there are many other metrics that we need along with what we call quote performance metric, and so a complete characterization of quote performance of that system has to include such things as reliability, right? Otherwise you will end up with a product which is very fast but doesn't work. What good is that, right? I mean, it came with 500 gigabyte per second, but it worked for 1 day. And so your boss will fire you the next day. And so, all right, so that's the kind of thing. So we will have a whole chart, flow chart, which says how do you find the right set of metrics. Second part is measurement techniques and tools. Here we will talk about lots of stuff here, but actually there is a lot of things on the list here, but most of these are in the book. We may not be able to talk in the class about all of these, but let me just go through the list here, and they're easy to read. First is, what are the different types of workloads? So there is a dry stone, there is spec, there are many different kinds of workloads you may have heard about. If not, you will hear about. And why should one use this or that? Popular benchmarks, and these are some of the names that I mentioned a minute ago are popular ones. The art of workload selection. How do you select the right workload? How do you characterize the workload? So basically, one of the things that you may have to do is to measure the workload. Say if you are working for Facebook, I mean, there is no workload that is known beforehand. You have to measure it on the real system today and then use it for tomorrow. And if you are working for a bank, maybe there is a system that some other bank had already measured, so you can just use a standard thing there because those things are very standard. So like that, you have to do characterization. Means you have to measure the workload and somehow characterize it. Say, well, this is what the workload looks like. Monitors, which is basically part of measurement. Accounting logs, and those actually turn out to be the most easiest way to get the workload. Is you go to the Facebook accounting and see what people have done, how often, and how often they make a new friend, how often they do this, how often they do that, and then you get a workload. Monitoring distributed systems. That's basically a problem because every system, one system is here, one is over there, how do you coordinate and all that. Load drivers. And then last problem is in the measurement is that you really have to drive a system with thousands of users. So let's say you're designing a system for Facebook. They have millions of users. Maybe 1 billion, I don't know. So the idea is we are given a lab, performance analysis lab, you are in charge of performance analysis. And now you have to drive this system where you find 1 million or 1,000 or even 100 users. How do you do? Yeah, exactly. So the thing is, so we do a load driver, which means that we set up a system which looks like 100 users, 1,000 users. You put a number 1,000, it's a big system. It can produce 1,000 random commands of different types that you have programmed in the workload. So basically we wrote lots of remote terminal emulators in my days. And so those are the load drivers. Capacity planning we already talked about, and then the art of data presentation. Now the main thing is that your analysis doesn't stop at the measurement or modeling. You have to present it, and if you didn't present it right in the industry, it is useless, totally useless, because it's your waste of your time and waste of their money to hire you if you didn't present it right. Because you have to present it so that they can understand. And finally, the ratio games. So how do you show your performance? Game. I use the word game here in the sense that how do you? In a lot of papers you will see that they present the performance of the system looks much better than the other guy. All right, but if you just change little bit, same data, just change the way you analyze it, and it turns out that they are worse than the other guy. Right? So I noticed lots of such games in some very respected papers, and so I have a chapter on that. So example, which type of monitor, software monitor or hardware monitor? So here monitor doesn't mean a display. A monitor means a measurement thing, right? Software monitor, hardware monitor would be more suitable for measuring each of the following quantities. So you want to measure the number of instructions executed by a processor. What will you use? Hardware monitor or software monitor? Hardware. Why? Yeah, the speed at which things are happening, right? Degree of multi-programming on a time-sharing system. Everybody knows what is the degree of multi-programming? Okay, number of processors running on the system. So what do they call them? I mean, if that should be kind of obvious for the computer science people. Is there another name for it? Okay, well, here's the thing. Maybe I am a little bit out of date on this, but in our days we had just started multi-programming, time sharing. Before that there was no time sharing. You ran your program, one program, and that's it, done. If you wanted to run 2 programs, there was no way. Well, actually it was before my time. But anyway, so the thing is, when they started running 2 programs, and this was called Multics, by the way. Multics is multi-programming, for multi-programming and all that. And so that was a invention. And one of the important things, how do you do multi-programming? How do you do, and Multics, and then after that came Unix. Unix is actually named after Multics. It's a copy of Multics. So Multics, Unix is play on Multics. And Unix is very popular. It is a multi-programming system, but I don't remember now what U stands for. Maybe it is universal or whatever it is. But basically, it took all the technology that was developed at MIT and Multics and then put it into the real world. All right. So done that. So multi-program. How do you measure the number of processes running on the system? You want to know whether there are 300. I mean, basically, generally on a real system, you are not really measuring the number of processes. You might be more interested, rather than this, number of users on the system. right? So how do you measure that? Hardware or software? Yeah.
Software.
Huh?
Software.
Why?
It's countable.
Yeah, it's probably not easy to do it by hardware. The hardware memory doesn't know. I mean, the CPU probably can count, but it will be software, right? I mean, that's good. And then I'm not going to go through the response time of packets. Okay. Probability theory and statistics. Now, this course is on performance analysis and modeling. So that is one thing I want to warn you. There is a lot of statistics here. I'm not assuming that you know a lot about statistics, but if you have never heard of a random number, you will have difficulty. Because this cannot be your first course. Generally, that level of statistics is taught in the high schools, I assume. And so I will tell you in the next slide, actually this slide itself has some of those things, as to what are the things you need to know. And that might be a showstopper, in the sense that if you don't know, then in spite of everything else, you may have to wait until you have taken one course in something. All right? So probability and statistics. So 4 important distributions. If I say normal, uniform, you have to know what normal is, what uniform is. All right? Summarizing major data by a single number. So when you get 1,000 numbers or you get a whole sheet full of numbers, you measure the number of users, and for a day you will get 1,000,000 numbers. You're not going to present to the management and say, look, I measured it and here is the list. They're not going to look at the list. They don't need the list. What they need is one number. How do you do that? How do you do that? Summarizing variability of the measured data. So you say, well, the average is 64. So how good is that number? Could it be 64,000? The answer is yes. Then 64 makes no sense to me. Right? Can it be 100? No, sorry, it is very close to 64. Then yeah, this is a good number. And so we have to worry about how variable that number is. Graphical methods to determine distributions of measured data. And often you have to say, well, this thing is normally distributed, this thing is exponentially distributed. That was the third distribution, which is very common. This thing is, whatever it is. So how do you find out whether it is distributed like that? So you have to do the distribution. And we will teach you how to do that. Sample statistics, confidence intervals. So confidence intervals we will teach again here in the class. Comparing 2 alternatives, we will teach you how to compare 2 different things when, again, there is a lot of variability in both systems. Measures of relationship. So how do you know whether this thing is related to that thing? Like if you increase the number of users, something changes. Maybe response time goes up or down. So what is the relationship between the two? Simple linear regression model. So straight line fitting. All of you know straight line fitting. Probably they teach you in high school again how to fit a straight line. That is called regression. But we teach you all over again in this course. For 2 reasons. First of all, we teach you so that you do it statistically correctly. Second thing, there are lots of concepts about testing your models, checking your models, that I find it very easy to explain with regression, and then we use them throughout the rest of the course. Multiple linear regression models and other regression models. So by the way, all this list here was, you really don't need to know, in the sense that this is what we will teach. So we will teach you 4 important distributions, how to measure the data by single number. This is all in this course. But if you have never heard of a random number, that would be very difficult for you to understand any of this. Alright? So here is the example. The number of packets lost on 2 links was measured for 4 file sizes. So we took a file of size 1000, and let's call it 1000 megabyte or 1000. Nowadays, in my days it used to be kilobyte. Now it is 1000 megabyte. Or actually, it already says packets. So 1000 packets. We sent 1000 packets, and on the link A, 5 were dropped or lost. On link B, 10 were lost. All right, that is our first workload. Second workload, 1200 packets file was sent, and 7 were lost on link A, and 3 were lost on link B, and so on and so forth. Which system is better? Link B is better for big file size, 1300 it is not. Oh, better, it is better actually, last. Okay, 3 is better, 3 is better, 10 is not good. So you are saying 1000 maybe, okay, I mean that's, okay, so that's a good observation. That is one of the observations, but there are other ways to say this thing, and we will explain to you, teach you exactly how to say and then justify your answer. So the biggest thing is, in the real world is, it's not what you say, but how you justify it. There could always be a different answer, because that's why my book is called The Art. It's not a science. Everybody sees, the beauty is in the eye of the beholder. So the answer is in the eye of the beholder. What is the right answer is in the mind of the person who is telling the answer. And we may not agree, but if you can justify that this is why I think this is right, that's most important. If you yourself have no idea, then obviously you cannot sell it. Right? So you have to know how to find the right answer your way, and then do it. Part 4 is experimental design. Now, what is experimental design? I don't know of any other performance analysis book in computer science which talks about performance experimental design. However, we introduced it in 91, and now there are lots of papers I can show you which use this. And most of the projects that we had done in this class in the past, they used experimental design. And most of the projects that I taught at other places before this university, they use experimental design. And the reason is, here is the problem with the experimentation. What is an experiment? First of all, if you are doing a simulation, you have to run 1,000 different cases, because the parameters are different, so you have to see the effect of the parameters, different parameters. So that is, each simulation is an experiment. If you are doing a measurement, you have to probably do at least tons of measurement. You cannot do 1,000, but at least you can do hundreds. So each of those is an experiment. And just like there is always shortage of money, so ideally you would like to do 2 million experiments, but obviously they don't have money and they don't have time to, you don't have time to do it. And therefore you have to find what is the minimum number of experiments that I can do. So will answer come out, well, you can do maybe 15 experiments and then you will get most of the answers. So that is one part of the experimental design, is to find the minimum number of experiments that will give you the answer. Second part is which 15. Now there are 1,000 possibilities, so you have to find the right 15. Third thing is, if you find the right 15, how do you analyze it? How do you get that information that you're looking for? So that is called experimental design and analysis. So all of these words here will be totally foreign to you today, so don't worry. Basically we'll teach you what is a 2 raised to k factorial design, what is 2 raised to kr factorial design with replication, 2 raised to k minus p fractional factorial design, what is 1 factor experiment, what is 2 factor full factorial design, and so on. All of this is new stuff. I don't think you have learned that in the high school. So this is something that you have to wait. So here's an example. Performance of a system depends upon following 3 factors. Garbage collection technique. Anybody knows what is garbage collection? Some people know. Okay. So basically when you use the memory and the program goes away, the memory has to be somehow collected back. And generally the systems will wait for a time. Just like in our offices, they don't collect garbage every second, they collect in the evening. So there has to be a garbage collection cycle in the computers when they collect all the memory, put it back into for use. Alright, so we have three techniques, G1, G2 or no technique. Type of workload could be editing, computing or artificial intelligence. Type of CPU, C1, C2 or C3. So there are 3 factors and 3 possibilities. How many experiments are needed? Well, one answer would be we need 3 times 3 times 3 27 experiments, all possible combinations. But if I just increase the number 3 to something large, right now it is 3 raised to 3, I could give you 10 factors and 10 experiments, 10 possibilities each, that would be 10 raised to 10. And then what? And not only that, you have to, measure it, you have to analyze it, so to figure out whether it is the CPU which is causing the problem, is the workload which is important, or is it the garbage collection technique which is making a difference. If you are designing the garbage collection techniques, you are not even going to think about any of the other things and say, well, wait a minute, my technique is the one that really does everything. All this performance is because of that. And that may be true or may not be true. It could be the workload. That you selected a workload that is good for your system. Just like, she said that, it was good for the big packets. So maybe it was the thing that you just didn't use the small packets. So simulation. So it turns out in research in particular and in the advanced product design in the industry as well, most of the time that your thing that you are going to measure is not there at all. So the computer, the database system, the algorithm, thing that you are designing is not there. It's just in your brain. And so what you do, you have to do simulation. So simulation is the most common technique used in the life cycle that we are in, most of us are in. Some places you can do measurement, but those places are very limited. Some places you can do queuing theory, but that is only for the professors. Most people cannot do that. And so really simulation turns out to be the main thing. And so we will teach you about the simulation. What are the different types of simulation? How do you verify and validate the simulation? And these are two different words, verify and validate, and we'll talk about that. Analysis of simulation results. And just like workload affects the performance, another thing that affects the performance of simulation is random number generation. If you have a wrong or bad random number generator, your results will be wrong. So that is the key. So we talk about testing random number generations, and then random variate generations. What is the number and what is the variate? Number is basically what happens when you want to generate a random number is you generate a uniformly distributed number, and that is called a random number. And then if you need a normal, you do something with it and you get a normal distributed number. That is called a variate. So anything which is not uniform is called a variate. And commonly used distributions. And then we talk about some of the common things like exponential and Bible and so on and so forth. We will not talk about those in the class, of course. They are talked about in the book. But it is important that you read that part so that when the time comes, you know some of the things that are in that chapter. Yeah.
Can you explain again what is a variate?
Okay. So we use the term variate for those random quantities that have a distribution other than, if the thing that I generated like this, that is a random thing, right? But if we generate many of these and if it is uniformly distributed, then we call it random number. And all in the simulation, most of the time we just generate the random number first, which means we generate a uniform number first. And then we do some calculation on it, like take exponent of it, or take a log of it, or do something to get other distributions from the same thing. So the key is the random number generator. Random number generator gives you a uniform number. So here's an example. In order to compare the performance of two cache replacement algorithms. So here is one more thing. Let me just say throughout this course, there is a lot of statistics, but this is different than the statistics course. Because if you go to statistics course, they don't know about computers, and their algorithms would be, their examples would be very boring in that sense, for you, right? Here, this is designed for computer science. We have no other examples. We don't take examples from medical field. We don't take examples from agricultural field. We don't take examples from any other field. Everything is computer science, and this is what we have used. Most of the things that we are here, actually, I have in the book, I have two kinds of things: examples and case studies. Case study is the real thing, in the sense that somebody did that in the real world. every number is real. Every problem is real. Examples are something that I made up. Okay? So that is the difference about this, is that we have tried to apply these techniques to the real computer systems, and we have come into the issues that other people may not have come into, and we have resolved them, and so that's what we are going to teach about. Is so the reason that thought came to my mind is because it says cache replacement algorithm, and you could do simulation of many different things, but here everything is about computer systems. So what is a cache? So before you put into the memory, which is kind of you have to get it from the disk or some place. So actually the other way around, is that if you have to go to the memory, it might be slower, so you put into the cache. It is much faster memory. And the thing is, it's faster, it's expensive, and therefore it's a small, and so it's quite possible that it becomes full very soon, and you have to replace some of this stuff to put the new stuff. Everything has a cache. Even disks have a cache. When you read the disk, you don't want to go to the disk every time. You read it beforehand, put it into the cache, and when the cache becomes full, you throw out some stuff, older stuff, put the new stuff in. So the question is, what type of simulation model should we use? And right now we didn't even talk about what are different kinds, so I will not go into the answer. How long should the simulation be run? And that's another thing, is that you run the simulation, so do you run it for a day or a half day or 1 hour or 30 minutes? That's a very important question. I can read a paper and I can tell you that this guy didn't run the simulation long enough. And we will teach you those techniques. That's why it is called the art. And so that is, and we will tell you how to really find the right length. So that is another thing. What can be done to get the same accuracy with a shorter run? How can we decide the random number generator is a good generator? So all that. All right, the final part, queuing theory, and actually an important part. So we will talk about what is queuing theory. How do you analyze the queue? By the way, why we have to worry about queuing theory in computer systems? Jobs. Yeah, if you have processes running, you have 100 processes running, they are standing in the queue. Right, and you decide which one to be serving first. This is similar to, when you go to a supermarket or a bank, and you have to decide how many queues to have, and which things to be put in what queue, and how to take them out. So all that is, so there is lots of queues. Every single resource in the computer has a queue. The disk has a queue, the memory has a queue, the CPU has a queue. If you have a network, it has a queue. And so the whole performance is queuing theory. So queuing networks, then something called operational laws, and that is what I really want to teach, because operational laws is what we call back of the napkin calculations. Most of the courses in queuing theory, they teach you a very deep queuing theory stuff. Some of the things that I even cannot read without going crazy. It's so much equations. But really in the real world, what works is something that you can explain to your boss on the back of the napkin. And there are techniques that will give you that kind of information. And so that's what I want to explain. Operational laws. Mean value analysis, that goes a little bit more mathematical, convolution theory, and advanced techniques. So we will probably not get that far, but this is all in the book. We will probably get up to operational laws, and if time permits, an MVA, mean value analysis. Here is the example. The average response time of database system is 3 seconds. So you did the measurement, and you found out that your database system takes 3 seconds to answer the query. You ask, what is my balance? And it tells you in 3 seconds. During 1 minute observation interval, the idle time on the system was 10 seconds. And then you observed it for 1 minute, 60 seconds. Out of that, it was busy for how long? 50. And 10 it was idle. That's all you know. Now, can you tell me what is the system utilization? What is the average service time per query? What is the number of query completed during those 50 during that minute? Average number of jobs that were in the queue in the system. What is the probability of the job system being more than 10? What is the 90 percentile response time? What is the 90 percentile waiting time? All of these things. Can you tell? The answer is yes, under certain assumptions. What are those assumptions? So we'll talk about that.